minus vt, just one variable, right? Not two. Now, in the opposite direction, if the wave instead of propagating in the positive x direction as shown here, but instead if it propagates in the negative x direction, then y is instead f of x plus vt, right? Because now the pattern will shift toward the left. So this is how the pattern goes in the wave. So at this point, is there anything unclear, or should we? So basically, we just realized that the wave function y, right, is just a function of not x and t independently, but just this linear combination of x and t, and that is because the waveform remains the same, but just shift in time at constant speed v, at which the wave propagates. Now, if we are good, we can move on. Okay, so with this definition, we can look at something a little more general, right? A little less household example, right? So if we keep shaking the string, but a little more regularly, then we get a wave pattern and look something like this, right? So in particular, at time t, the wave may look like the blue line here, right? Which is this line, in case it is not so clear. Okay, so it is this line, and then the other way around. When t is 0, it is the red line, which is this line. And then at some other time t, right, the wave pattern would travel, in this case, toward the positive x direction, and it travels with speed v, right? When it does that, we see that the wave shifts from the red pattern to the blue pattern. So it is the same pattern, but it just shifts in position over time with constant speed, right? So here, if the elapsed time is t, then the wave would just travel the distance vt over time, meaning that, say, the peak on the top, it just moves the distance vt over time t, and so on. So it just keeps moving to the right. Here with this wave, you can define a few parameters that describe its shape and in turn give you the function, right? Give you the wave function y. The first thing is the amplitude, which is basically, if you remember from last time, right, it is basically the distance between the equilibrium point, y equals 0, to the maximum displacement in y in either direction, right? So basically it is the maximum distance of an element in the string or in anything in the wave medium. It is its maximum distance away from its equilibrium position of y equals 0. And also the wavelength here is basically the distance between two crests. So it is the distance between two peaks in the red or in the blue, but in the blue you only see one peak anyway. But like, say for the red you see two different peaks. The distance between the two peaks is the wavelength, lambda. And we see that you can have different lambda depending on essentially how compressed the wave pattern is, right? Or how frequent the peak occurs. And the wavelength is directly is kind of related to the frequency here, right? Which is, well, we can even talk about the period first, just follow the order. So the period is the time interval between. So if we have two peaks in the red, right? Say if we are here, right? We see one peak passing through one red. Now, if we are here, right? We see one peak passing through when t equals 0, and then we wait until t is capital T, which is the period. That is the time we see the next peak passing through the same position. So if we let the time pass, right, and we time the interval. We time the interval that it takes for two neighboring peaks to pass through, then that is the period of the wave. when you stay at a fixed position x0. And then the period is basically the reciprocal of the frequency. That is, if we stay at some position x0 again, then we stay there for a unit of time, say a second, a minute, or an hour, and we count the number of crests, the number of peaks that pass through you, right? And that will give you the frequency. And we'll see that, say, if we count how many peaks pass through us in an hour, right? Then the reciprocal of that, if we see 6 peaks passing through us in an hour, it means that the period of the wave is a sixth of an hour, which means 10 minutes, right? So that means the frequency and the period are the reciprocal of each other, right? And as a result of that, we can write f to be 1 over t, and then we can define the unit of the frequency f, which is the inverse of a second in SI unit, right? The standard unit. And the inverse of a second is usually called hertz. And that is if you, I'm not sure, I don't think people listen to radios anymore, but when you specify which radio channel to listen to, you usually specify the frequency in megahertz, right? And in standard notation, the amplitude, which is the distance here, is usually represented by A. The wavelength, which is the distance from this peak to this peak, is represented by lambda, which is this Greek letter right here, right? And the period is capital T, and the frequency is lowercase f. So in terms of these variables, we can define more stuff, right? But before that, we just consider what the wave function would look like. Well, we know that given the amplitude A and the fact that the sinusoidal function sine or cosine is between -1 and 1. Well, this is the shape of a sine function, right? It's quite clear. Now, if the sine goes from -1 and 1, we know that the wave goes from -a to A, right? And that is because that is the definition of the amplitude A. Then we can write the wave function as A times a sine function. And what goes inside the sine? Well, that to see that, we have to go back to this consideration, right? If the wave propagates toward the positive x direction, then we know that the wave function is a function of x minus vt. So in general, we must have sine of some constant times x minus vt plus basically a phase, an initial phase. And the initial phase here, which is another Greek letter phi, it is defined such that the position at the displacement y at position x equals 0 at initial time t equals 0 is just a sine phi. So that if we know the amplitude A and we know the initial position y0, 0, we can usually determine phi up to some sine, right? So in particular, for example, if we know that y0, 0 is exactly the amplitude A with the plus side, then the initial phase phi must be pi over 2, because sine of pi over 2 is 1, right? So that is, we just solve the equation right here. Now, here we have, so for this case, we have x minus vt because the wave is propagating in the plus x direction. Well, if the propagation direction is opposite, if it goes toward the minus x, then this must be x plus vt. But that is, or even more conveniently, you can replace x by negative x. So we just flip the coordinate x, right? So okay, this is great, right? We're getting close to writing down the wave function for
sinusoidal wave or the sine wave.